Over the last 100 years, the theory of special relativity, despite inconsistencies with other theories, has dominated much scientific thinking. The theory has a beguiling beauty, but that does not mean it is correct. In this short presentation, we will illustrate how the theory can be challenged. In doing so, we will argue for a return to absolute rather than relative measurements of space and time. We present here a brief summary of the main points of a short book by Francis Pym and Clifford Denton. The full text of the book is available to read online or to download from the website www.absolutespaceandtime.com. During the 19th century and early 20th century, there seemed to be a strange result every time the speed of light was measured. It did not seem to be like measurements of the speed of sound. If we measure the speed of sound, we know that as the transmitted sound moves through the air, we must deduct our velocity from the velocity of the moving sound waves to obtain the velocity of the sound waves relative to us. If the vehicle from which we are making measurements moves towards a wall from which the sound is reflected, the vehicle moves a short distance before the sound reaches the wall. The speed of sound on the outward journey, as measured from the vehicle, is the speed of sound in still air minus the speed of the vehicle. On the return journey of the sound wave, since the vehicle is moving towards the echo, the apparent speed of sound will be the speed of sound in still air plus the speed of the vehicle. When it came to measuring the speed of light, similar experiments were carried out. If there is a medium for carrying the light waves, analogous to the air which carries sound waves, a similar result would be expected when the apparatus moves through the background medium. Of course, the very high speed of light made it necessary for more sophisticated apparatus, but the nature of the experiment was the same. Light was considered to be travelling in a background medium that pervaded all space, known as the ether, and attempts were made to see if two-way passages of light, from transmitter to reflector and back, were affected by movement through the ether. The result of these experiments with light were unexpected and could not be explained through conventional physics. The apparatus for measuring the speed of light could be likened to the car moving towards a wall, measuring time for the reflected transmission. The only difference was that the reflector moved with the apparatus. Nevertheless, it would be expected that movement through the ether would be detected. We would expect measurement of the speed of light to decrease with movement through the ether. This was not so. The speed of light seemed to be independent of the movement of the apparatus, casting doubt on the existence of the background medium. Progress in this area of physics came to a halt because of this strange result. When Einstein formulated the theory of special relativity, he thought he had discovered a way of making progress. He tried to bypass the experimental result. What he did was to redefine measurements in space and time that has left science with the legacy of special relativity theory up to the present time. Progress was made of a kind, but progress which is based on two questionable assumptions. Einstein found a way of ignoring the so-called ether. His theory did not require us to know whether it exists or not. Since remarkable progress in physics seemed to be possible, few scientists have thought it necessary to challenge Einstein's assumptions, and it has even been considered naive to argue the case for a background medium. Nevertheless, in their book Absolute Space and Time, Pym and Denton proposed that it is entirely plausible that a background medium to the universe exists, through which light travels. The exact nature of this medium still raises questions, of course, so rather than call this medium the ether, they derived a different terminology. This terminology reflects the view that there is a domain of rest through which physical bodies move and from which absolute measurements can be made. This takes us back to the time when scientists such as Michael Faraday were investigating electromagnetism and proposing theories for the transmission of electromagnetic waves through the universe, based on absolute measurements from such a medium considered at rest in the universe. Let us now consider the two assumptions on which the theory of special relativity is based. The first assumption in Einstein's paper on special relativity confronts head-on the issue of the background medium in space. He proposed that not only the phenomena of mechanics, but also those of electrodynamics have no properties that correspond to the concept of absolute rest. In other words, Einstein, realizing that the so-called ether could not be detected, decided to found a theory on the assumption that even if it did exist, it had no bearing on the way physical bodies move, are measured and interact. He proposed that a background medium was irrelevant. The second assumption states that light always propagates in empty space with a velocity c that is independent of the state of motion of the emitting body. All experiments to determine the speed of light measured the time taken for light to travel to and from a reflector along a measured distance. It was always a double journey, to the reflector and back. It is not possible to find the speed of light in one direction. Einstein decided to assume that the speed of light is constant in any direction from the results of the experiments on a two-way passage of light. A third assumption, which really depended on assumption 2, relates to synchronicity of clocks. If synchronous clocks which start in one position are moved apart, we have no way of knowing if they are changed by the motion and remain synchronous. To check synchronicity, a signal concerning clock B's time has to be transmitted from clock B to an observer who is at the position of clock A. Einstein's definition of synchronicity depended on the assumption of light travelling from A to B at the same speed as from B to A, whether or not the clocks were moving through the ether. If motion does influence the speed of light as perceived by bodies moving through the ether, or, as we have called it, the AFR, then Einstein's definition of synchronicity is wrong. Indeed, it is the very assumptions of special relativity that redefine measurements in time and space as variable quantities, depending on relative motion. By assuming that the velocity of light is unchanging, change is attributed to other physical quantities of space and time as we formulate the equations of physics. Our proposals based on absolute measurements from an AFR are subtly different. The well-known Lorentz transformation equations were adopted by Einstein. They are the result of the idea that each moving body is in a sort of universe of its own, and the equations allow us to calculate what different observers in motion will measure for length and time, as if these are variable quantities depending not on an absolute reference point, but on relative motion. No account is taken of the influence of an ether or AFR because the existence of such is ignored. Yet surely we cannot ignore an AFR if it exists. Thus, Pym and Denton proposed that motion of the particles that make up a physical body interact with the AFR, causing shrinkage in the direction of motion. The particles move closer together due to motion. This could be related to the speed of transmission of information between constituent particles being affected by the motion. This information, transmitted between particles, is the basis of what we call force, and the result is shrinkage to preserve the time of transmission of the information. This interaction between particles and the AFR also causes clocks to slow due to motion. These theories are argued more fully using some simple mathematics in the book by Pym and Denton. Though at first sight there seems only a slight difference in perspective from special relativity, the difference is one founded on a different approach and not on assumptions which carry with them potential for errors. Special relativity states that time is measured differently by different observers depending on their relative motion. Time becomes a variable in equations of special relativity. We propose that it is not time that changes, but the measurement of time changes due to the interaction of clocks with the AFR. Special relativity states that length is measured differently by different observers depending on their relative motion. Length becomes a variable in equations of special relativity. We propose that motion through the AFR causes actual change in the physical length of physical objects. Based on this, let us now look at the reason why experiments have failed to detect a change in the speed of light due to motion and, as a consequence, failed to detect an absolute frame of reference, AFR. In Chapter 5 of their book, Pym and Denton show how the length contraction due to motion is by a factor phi, and that clocks in motion slow by a factor phi. This, at first sight, seems to be the same as in the theory of relativity, but these are not relative measurements according to the Lorentz transformation, but actual measurements due to motion in the AFR. We now consider a piece of apparatus moving at speed v in the AFR. A and B are the transmitter and reflector in the moving apparatus. A sends a light signal to B and B reflects it back. The time of the two-way passage of light is measured and the distance AB is known. The following discussion is found in Chapter 7 of Pym and Denton's book Absolute Space and Time. As has been demonstrated by experiments, let us now show why the speed of light is always found to be the same numerical value c, masking the fact that its speed can vary for one-way travel in moving objects. In this discussion, we must be careful to note that instruments at rest in the AFR record measurements that are absolute, and that instruments moving with the body AB record measurements that are not absolute. In our discussion, T0 is the time measured by instruments stationary in the AFR, L0 is length as measured by instruments in the AFR, and c is the speed of light as measured by instruments in the AFR. T0AB and L0AB is our notation for time and length as recorded by the moving instruments. Suppose AB is moving at speed v, while light is transmitted from A to B and reflected back to A. The light travels parallel to v at speed c in the AFR. Due to motion, it is received at B at speed c minus v and at A at speed c plus v. First, let instruments that are stationary in the AFR determine the speed of light for AB. Distance AB is measured by instruments stationary in the AFR as contracted length L equals phi L0. The absolute duration T0 for the two-way parallel beam of light reflected over AB will then be timed by a clock stationary in the AFR. The total time T0 for the two-way parallel beam of light that travels from A to B and back at different speeds over shortened distance AB will then be equal to the equation shown. Adding the two times gives this. Since c squared minus v squared over c squared equals phi squared, c squared minus v squared can be replaced by phi squared c squared. Then the expression becomes this. Or, by substituting phi squared for c squared minus v squared over c squared, we simplify to this expression. Simplifying again gives us the absolute time for the two-way travel of light A to B and back. However, since AB is moving, this expression of time for AB, which is now this, should be multiplied by phi for clock rate change so that it becomes the following. This gives the value of the time seen from the AFR but measured by a clock moving with AB as follows. Next, instruments travelling with AB will be unaware of any movement through the AFR and will measure the contracted length as L, which the AFR sees as being phi L0. However, rulers moving with AB contract in the same ratio as lengths being measured. Then instruments moving with AB but viewed from the AFR will obtain the value for the length AB as follows. And for the distance for the two-way journey of light A to B and back as follows. So, according to the units of length and time on the measuring instruments that are moving, the value of the average speed of light for the two-way travel, total distance over total time, is as follows. The constant, numerically the same value of c, is derived here by instruments moving with AB using units of length and time that are affected by length decrease and clock rate change. Thus, although the speeds c minus v and c plus v of one-way journeys of light between A and B are different, the overall average speed is constant for this and any double journey. We stress again this important observation. The speed of light averaged over a two-way journey to a reflector and back is found to have the same value that we denote by c, whatever the speed of the moving instruments. This is because the measurements of time and length change with motion when compared with absolute measurements made from instruments stationary in the AFR. The duration of time is thus longer at TAB and lengths are shorter at L0AB, but it is not perceived by the instruments in motion. Interestingly, this calculation produces the same value for the speed of light. Pym and Denton also show that the familiar equation E equals mc squared, which is attributed to Einstein, is derivable in a simple way using absolute measurements in the AFR. The result is not dependent on special relativity. This has been a brief introduction to illustrate the way the beguiling mysticism of special relativity theory can be replaced by concepts based on absolute measurements without losing the valid results of the theory. We're grateful to Einstein for making a way forward when physics was stuck because of difficulties in explaining experimental results relating to the velocity of light. Now, we suggest that it is time to return to absolute concepts without losing these valid results.